well, let's take a look. We got one more theorem to prove, and let's see what it looks like. So we'll just rewrite it out here. We called it, I think, 3.5. So we'll just write it in sort of a shorthand here because, well, we got to get down to it. Okay, so theorem 3.5 basically said that, like, if you have the product of two matrices, det A, B, you can sort of take each of them separately. And so we know this for elementary matrices, but now what we want to prove is, like, well, does it work for any old matrix that you want? And maybe some of us, the way that we proved the last theorem, maybe we have an idea of how we're gonna proceed here. So let's take a look at the proof. And we're going to lean heavily on those sort of corollaries that we looked at. Okay, well, we're going to do this, if anybody remembers from like way back at the beginning of the year, we're going to do this by cases. We're going to say, like, okay, let B be invertible. Okay, so we're going to assume that B has an inverse, right? Okay, then by 3.8, right, we can write B as the product of elementary matrices. Okay, well, B equals like E1, E2, En. Okay, and by 3.7, if you remember, we had that 3.7 that we said, like, well, if you have elementary matrices, you can factor them all out. So then we can say that the determinant of AB, well, that's really the determinant of, like, A times E1, En, right? And by 3.7, we can say, well, that's the determinant of A times the determinant of, like, E1, determinant E2, determinant En, right? Well, but remember, the determinant E1, E2, E3, this whole thing, well, this is just determinant B. So, okay, so now I've got det A, det B, and that's what we wanted to prove. So that's the first case. I'm going to put, well, a tombstone on it because they're fun. Okay, well, what if B is not invertible? Well, then AB is not invertible. And like before, the theorem reduces to 0 equals 0, which is in fact true, so we're okay there. Let me just, like, convince you that if B is not invertible, that AB, the product, is invertible. So let's say, like, I don't know how to label this, but we'll just say, like, fun fact. Okay, so let's say A, B equals some other matrix C, right? And B is not invertible, okay? Well, let's assume C is invertible and proceed by contradiction. Well, I've written that in the wrong order, but that's okay. We're going to proceed by contradiction and assume C is invertible. Okay? Right, because I'm telling you here. Sorry, this is going to be annoying for anybody who's writing it on paper. Oh, jeez. Really making a mess of this one. Okay, so I'm going to proceed by contradiction and assume C is invertible. Okay, then I can we can left multiply call this equation star, by C inverse, and well, then I've got C inverse AB equals C inverse C, right? Which, okay, and then you've got C inverse AB equals identity. Wait a minute. Then what I can say is then, well, this is a matrix. Times B equals the identity. What does that sound like? It sounds like C inverse A is B inverse, which is a contradiction. There it is. So yeah, so that was a little sidebar, but like now we know a couple of properties of the determinant. The determinant of a product of matrices is the product of the determinants, and what we proved here was the determinant of a matrix is the same as the determinant of its transpose. This is wonderful work. Okay, we're just going to do a quick summary, and then that'll be it. So let's see. I'm going to need a new page because there's a lot of stuff to summarize. Okay, I don't want that page on there. Okay, so summary of properties. Again, we haven't, it's a bit strange the way we're doing this, but it's, you know, the book is called Linear Algebra Done Wrong, so it's gotta be a bit strange. We've sort of like figured out all these properties that we want our determinant to have and some ramifications that may proceed with, and we still haven't exactly talked about, well, how do you formally define it, and like how do you actually calculate it on some matrices that aren't simple. And what's nice about it is when we go to do those things in the next day or video or whatever, we can sort of build it out of these properties, and somewhat clearly it's going to come into focus. So we're just going to summarize real quick. The determinant is linear. I'm just going to say det for determinant is linear in each column. The determinant is, that's a good start, in each column. When others columns are fixed. Let me zoom out just a little bit. Are fixed. Okay, that was one of the first ones that we sort of ran into. That one came from like the parallelopipeds and all that other stuff. If we interchange two rows, determinant changes sign. Okay, third property, for a triangular matrix, and diagonal, right? Its determinant is the product of diagonal entries and note that out of this spills that the determinant of the identity is always 1, right? Because like, well, all the diagonal entries of the identity matrix are 1, and the product of a bunch of 1s, that's 1 too. Okay. If a matrix A has a 0 column, has a 0 column, the determinant equals 0. If a matrix has two equal columns, the determinant equals 0. Yeah, there's a lot of properties here. I get it. Okay, so 6. If one of the rows, I'm going to say columns. If one of the columns is a linear combination of two other columns, the determinant zeroes out. Right? And this is sort of where our invertibility became, right? Because if one of the columns in a matrix is a linear combination of two other columns, the matrix isn't invertible, and the determinant is 0. There was a pretty neat argument that we made there. Okay, the other one is like the determinant equals 0 if and only if the matrix is not invertible. Okay. Sort of similarly, well, the determinant is non-zero if and only if the matrix is invertible. Okay, and then 9. The determinant does not change if we preform, preform, I always spell that wrong, perform the sort of column elimination step, right, where we take some scalar multiple of a column and add it to the other one, and we sort of do that thing. All right, a couple more and then we're out, right? I want to talk, we're going to return to this one in a second. So the determinant of A equals the determinant of A transpose. These are the ones that we just did. Det AB. Let's see, 11 is det AB. The determinant of the product of matrices is this sort of product of the determinants. Oops, not det A to A, but det A to B. Okay, and then the last one, 12. If A is an n by n matrix, A times A, now let me say maybe the determinant of A times A equals A to the n determinant A. This last one is pretty neat. We actually didn't necessarily talk about it. I think it would be fun if you try to show it. This follows from the linearity of determinant. Right, and remember this thing here, what we're doing is we're multiplying every entry in A, in the matrix A by the number A. I want to do one quick thing before we get out of here or finish this video, or I don't know how this is going to go down, but number 10 has a really interesting series of ramifications. Because the determinant of A and the determinant of A transpose are the same, what that means is there's this weird similarity between column operations and row operations. So in all of the properties here where we talked about columns, so everywhere we have the word column written, oh geez, well, whatever. We could have written rows. Rows interchange with columns. So because the determinant of A and the determinant of A transpose are the same, if one of the rows is a linear combination of the other two rows, the determinant is equal to 0 because I just take the transpose and the columns become rows. So all of these properties have the additional thing if you think about it in terms of rows and if you think about it in terms of columns. That's a bunch of stuff, and we're going to use maybe not all of these, but a bunch of these to sort of talk about how we can actually pin down what a determinant is in the next video. Thank you.